Ladies and gentlemen, I would like to have your attention and let's begin this event. And let me welcome our distinguished guest, Professor Joel Spencer, today, who is going to, so to say, defend his honorary membership in the Hungarian Academy of Sciences. He's going to have an inauguration talk today. But before that, let me ask Professor János Pach, where is he? He is here, who is going to introduce him in a few words. So the floor is yours, János.
Okay, thanks. So, can you hear me? No? Okay. Joel Spencer is Silver Professor Emeritus at the Courant Institute of Mathematical Sciences of New York University and one of the foremost experts on the probabilistic method developed by Erdős. 50 years ago, together with Paul Erdős, he wrote the first monograph on the subject, which appeared with Akadémiai Kiadó Budapest. The modern version of this book, written jointly with Noga Alon, is the Bible of the probabilistic method. Together with Ron Graham and Bruce Rothschild, he was the first to devote a monograph to Ramsey theory. Both books have gone through numerous editions and have been translated into several languages. By applying Lovász's local lemma, in 1977, he improved Erdős's classical lower bound for the Ramsey function. His result hasn't been improved to this day. In 1985, he published his most cited paper, 6 standard deviations suffice. He proved that every n-element set has a 2-coloring such that the discrepancy within each of the n fixed subsets is at most 6 times square root of n. This will be the last mathematical statement that I will precisely state. In 1987, in a joint paper with Eli Shamir, he was the first to apply martingale theoretic methods to the study of random graphs. A major breakthrough was his joint work with Saharon Shela in 1988, in which he combined probabilistic methods with the tools of mathematical logic. Together with Gábor Tardos, he characterized the threshold phenomena of first-order statements about random graphs. These works formed the basis of his book, The Strange Logic of Random Graphs. Together with Andres Semeredi and Tom Trotter, in 1984, he obtained the best currently known bound for the maximum number of unit distances in the plane. With Géza-Tóth, he determined the asymptotic behavior of the crossing numbers of random graphs in many scenarios. He discovered important connections between Erdős range evolution of random graphs, Brownian motion, and other physical phenomena. Together with Jennifer Chase and Christian Borks, in 2005, he described the phase transitions of various large networks. His entire career is closely related to the traditions of the Hungarian School of Mathematics, and a significant proportion of his co-authors are also Hungarian. In 1973, he edited and published a selection of Paul Erdős's papers under the title The Art of Counting. Although he has no direct family ties to Hungary, he has learned Hungarian to an excellent level. He was an advisor of the Budapest Semesters of Mathematics and a member of the International Supervisory Board of Rényi Institute. He is the founding editor-in-chief of Random Structures and Algorithms, has been an editor of the journal Combinatorica of the Bolyai Mathematical Society from its inception. In 1995, he was a Nachdiplom lecturer at ETH Zurich, and in 2001, he delivered the Erdős Memorial Lectures at the Hebrew University of Jerusalem. He's a fellow of the AMS and of SIAM. He received the Lester IV Award of the Mathematical Association of America and the Steele Prize of the American Mathematical Society. In 1994, he was an invited speaker at the International Congress of Mathematicians in Zurich. According to the statutes of the Hungarian Academy of Sciences, there is another category of membership distinct from honorary memberships. An internationally recognized outstanding scholar may be elected as an external member if he is a Hungarian citizen living abroad. Joel Spencer's work is so deeply intertwined with Hungarian mathematics that he almost meets these criteria as well. Joel, please, the podium is yours.
Yes, so the floor is for Professor Spencer. Joel.
Thank you. Nagyon köszönöm szépen. Excuse me if I say a few words to my Hungarian friends. So, kufuldi vagyok, de az biztos, de idegen nem vagyok. 50 éve jöttem ide, Erdős Pál 60. születésnap konferenciájába. 60 éves, az hihetetlen, hogy valaki olyan öreg és olyan erős. 3 év ezután jöttem meg egyszer 9 hónapig. Szerencsés voltam, hogy a hidegháború ellenére volt egy csere program, exchange program, az USA National Academy of Science, és a Magyar Tudományos Akadémia, so köszönöm nektek, köszönöm. Amikor érkezett, némi tehetségem volt, de valami történt. Miért? Talán a kávéházok, talán a kifli, biztosan a matematikusok, de felszálltam a magyar vonatra. My mathematical life truly began in 1976 when I came here to Budapest for 9 months. Nagyon szerencsés vagyok. There's so much in my life, so much beautiful mathematics, and so many wonderful collaborators, many of whom are here today. Dolgoztam Szemeredivel, Lovasszal, Baránál, Simonoviccal, olyan sok másikkal, olyan jó, Katonával biztosan. Azután majdnem minden év jöttem Magyarországba, és találkoztam sok magyar matematikussal USA-ben, vagy konferencia bárhol világban. Pach Jóska, elvtárs főtitkár Pach János, drága Sósvira jött fél évig USA-be velem dolgozni. Minden matematikai társadalom maga módszere van, és a magyar matematikai módszer én nekem a módszerem lett. Sajnos soha tanultam a matematikai szöveg magyarul, integral e to the minus 2x cos 3x dx, azt nem tudok mondom. Magyarul, so elnézés, ha beszélek a anyanyelvem. So I will talk just some of the things that I think are the highlights over the past many years. Let me remember many of the wonderful people that have passed away. And here I only named 3, but there were, of course, many more. Okay. And as Pach János said, I had quite a few co-authors. So this is the first year of publications, and some of them I had many others. But actually, at the end, the honorary ones, there were so many people that I really worked with so much, but somehow we don't actually have a joint paper, but they really influenced my work quite a bit. And I think I have a special honor or special notice. I believe, est monta tardos Eva, that I am the only one to have a joint paper with Tardos Eva and with Tardos Gabor. So on that, I am extremely proud. Okay. So let's begin in April 1946. It was a very important month for me, but much more importantly, it was the beginning of the probabilistic method, this coming from personal notes of Polybachi, Erdős Paul, but we all called him Polybachi, so I'm going to call him Polybachi. The paper actually appeared in 1947, but in his notes it was April 1946, and it involved Ramsey theory. So many of you here are very familiar with the general idea of Ramsey theory, which was then rediscovered by Erdős and Sekeres in 1931, 1932, from notes that Sekeres wrote many years later, that if you have a large number, it's actually very, very general, but in this particular case, if you have a large number of people, and each pair of people either knows each other or doesn't know each other, we assume that, then inside that, you'll find a substructure, a subset of people that are very uniform, and what that means in this case is you'll find a substructure where either everybody knows everybody else, a clique, or nobody knows anybody inside that substructure, an independent set. So that was Ramsey's theorem, as rediscovered by Erdős and Sekeres. But Ramsey was never interested in the actual numbers of just how big that had to be. In his papers, he just proved the existence. But for Erdős, worked many, many decades on finding just how big these numbers were going to be. And so in the original, it wasn't in Ramsey's paper, but if you look at the Erdős-Sekeres paper, you see that you will get a clique or an independent set of size 1/2 log n, base 2. And then in the paper that in 1947, which the idea was in April 1946, was that there exists an arrangement of these n people where there's neither clique nor independent set of size 2 log n. And this gap between 1/2 and 2 has been something that people have been working on ever since with some success, but not much. But I won't talk about that part. But the thing was not the result, but the proof, which was you look at a random set. So imagine that the n people, every pair of people just flips a coin to decide whether to know each other or not know each other. And you call that a failure if there is some large clique or large independent set. Well, of course, it might be a failure. Maybe everybody knows everybody else. All the coin flips came up heads. But the chance of a failure for any particular set of 2 log n, you have 2 log n people, you have 2 log squared n pairs, and all those coin flips have to come up heads. And so the probability of that is extremely small. On the other hand, you have n choose 2 log n possibilities for this failure, and the number of possibilities of failure times the failure probability is less than 1. I mean, you have to do the calculation. And so therefore, when you do it randomly, the failure probability is less than 1. But then comes, excuse my poor Hungarian, but I like to call it Erdős Csoda. So the Erdős Csoda is, okay, the probability of failure is less than 1, so therefore the probability of success is greater than 0, and therefore there absolutely, positively, definitely, like exists a configuration, because if the probability is greater than 0, it can't be the empty set, so there has to be some configuration that works. And this idea that you go from probability to absolute certainty was the center of the probabilistic method 80 years ago, and it remains the center even today. So let me go back. I know how to go back. Ron Graham, I think of the people that knew Polybachi in concentric circles, and maybe Nemoyan Sere and Vajok, that I feel like I'm in the second circle. But the first circle, as I look at it, Alazatosh Velamenum Serint, was that the first circle was all Hungarian plus Ron Graham. So Ron Graham, this wonderful American mathematician who was really very close and very supportive of Polybachi. And also, I mention him personally because I was very lucky that I had 3 wonderful mentors. The first was my high school teacher. There's nothing better than having a great high school teacher. And the second was Ron Graham. And the third, and here I'm not alone, was Polybachi, because Polybachi had this special thing. I've often tried to think what it was. I mean, Polybachi would take people that had talent, so the people already had talent, but then when you started working with him, something wonderful happened. At least that was the way it was for me, and many other people have said that was the way it was for them. So let me turn to my own best result, which was in 1985, I think, and I had returned to Hungary. I think this one was on IREX fellowship. Just a minute. Oh, how did this happen? Pilinat. Here we are. So 1984, and I had returned to Hungary, this time with Édes Kislányám, who is right here. It's very nice. And it was a wonderful 3 months. And Dani, Alanyám, went to the Kodai Zene Iskola, which was actually a wonderful, wonderful experience for her and for me to see her at this wonderful school. But it was also wonderful for my mathematics, and the Hungarian magic worked, and I proved my best single theorem. The original problem was with n sets on n points, but this is a different way of saying it. You have n vectors in n dimensions. All the coefficients are between -1 and +1. And what you want is a ±1 vector where all the dot products are smaller than constant root n. Now, why is that a natural thing? Let's imagine all the coefficients were plus or minus 1, which is in some way the toughest case. If you took a random vector x and you take the dot product, you get a Gaussian. And the standard deviation is square root of n. So the chance of being 6 standard deviations away would be 1 in a million. But what if n is 10 to the 20? Then you're going to have some outliers. You're going to have some outliers. So picking, and this has to work, my result was that you could get it less than 6 root n. Actually, 6 was just a constant, which has since been improved. With no outliers. That is, you could get all the dot products were less than 6 root n. So this was a case where the straightforward random argument of picking a random choice of pluses and minuses did not work. And I certainly suggest that you not read my proof, because the first proof was Nagyon Ügyetlen, maybe is the word. And then it got improved by many, many people. The first algorithm was by Nikhil Bansal, but my personal favorite proof, now there are about 20 different proofs, was by Levitt and Meka. So I want to just indicate what the algorithm is to find the x. And the idea is that you use floating colors. I'd like to say that this idea came from Beck Yoshka, though it's Joseph Beck, but it's such a natural idea. I mean, I learned it from Beck Yoshka, so I don't know. So the idea is you want the colors, well, the coordinates of x, the xi, to be +1 and -1. So you start that they're all 0. So think of this n-dimensional cube, -1 +1 to the, in n dimensions, you know, the square except in n dimensions, and you start in the middle. They're all 0. Well, now all the dot products are 0. That's great, you know, except that you have to get to one of the corners. So what you do is you start moving in randomly, that is Boolean, sorry, not Brownian, you start moving in Brownian motion. And then when one of the xi's reaches +1 or -1, then it's glued there. It just stops there. That doesn't work by itself. That doesn't work by itself. Because you'll still get the outliers. You'll still get the outliers. But what happens is, the Lovett-Make idea is you use a clever Brownian motion. So again, you're moving around Brownian motion, and when an xi reaches +or -1, that's it. It'll never move again. So now you're really in an n-1 dimensional hyperplane because the xi's can't move. But also, you're going along, and some of the dot products are going to reach, let's say, 5.5 square root of n. Okay, when they reach 5.5 square root of n, you say, uh-oh, that's really dangerous. That's really, so you say, we're not going to move it anymore. So what that means is, you've got a dot product that's 5.5 root n, you freeze it, that means you're going to move perpendicular to that vector so that the dot product stays the same. So you're going to move in the hyperplane that way. And so that's the idea, except it's actually more complicated than that because there's an end game. Once many of the xi's get fixed, you have to move to something else, similar but something else. But, you know, today I'm just going to give the idea of the argument. So this was a use of Brownian motion that's just very, very powerful. In an algorithm, you can make it in discrete steps, and it's the same thing. Okay. Let me turn to another thing that I think was really fundamental. There are not many areas of mathematics where you can say they started right here. But I think you can say that with the theory of random graphs. I think it's fair to say that it actually started in 1960 with Polybacci and Alfred Rainey, both at the heights of their powers. And they wrote a paper, they actually wrote several papers, but their magnum opus was the evolution of random graphs. So in a sense, you look at the random graph with edge probability P, and P starts at 0 and it starts increasing. Or you can just add in edges one by one. That's very similar. And then at certain points, things happen. You get threshold functions. For example, when does the graph become connected? Well, of course, it could become connected most any time because there's probability. But most of the time, in a way that can be made formal, it becomes connected where P is around n inverse log n. That is where the number of edges is n squared over 2 times that. And if P is smaller, much smaller than that, the graph will, with high probability, not be connected. If it's much larger than that, with high probability, it will be connected. Similarly, planarity is around 1 over n, is where planarity, at the start it's planar, but it loses planarity at 1 over n. Or, for example, the existence of a K4, 4 points with all 6 edges. That occurs around n to the minus 2/3. And they had many, many more. But a critical thing that really has a life of its own, is what they call the double jump. So let's suppose that P, we parameterize P by C over N. So the way to think of this is that the average degree is C. And then it turns out, as they showed, that there's very different behavior. There is what looked to them to be a trichotomy. If C was less than 1, what physicists would call subcritical, all of the components were very small. They were all just trees or maybe unicyclic, but still quite simple. And even the biggest ones was of size log n, so real, just tiny little components. But if C was greater than 1, then what the physicists would call supercritical, there would be a giant component which would have a positive proportion of the points. So suddenly, these small components would merge and form this giant, not all of them, because the giant component wouldn't be size n, it might be size 0.1 n, but it would be, and that constant depended on what C was. And you'd have this giant component, and other than the giant component, it actually looked like it was subcritical. There were only tiny little components. And if C equals 1, well, these were two very smart people, and they worked very hard on the C equals 1, and it was a very complex behavior where the largest components were of size on the order of n to the 2/3, and they said a lot more about that. But it was very complicated work. Well, was that it? Well, people thought it was it because either C is less than 1, or C is greater than 1, or C equals 1, right? Well, wrong. That turned out that it wasn't a trichotomy, and the great breakthrough was made first by Bela Bolobash and later by Thomas Wuczek, and then by many, many people jumped in. And it's what's called the critical window. And again, for physicists, there are a lot of analogies to percolation, that what you should do at 1 over n is add a second order term. And the second order term should be parameterized lambda n to the minus 4/3. It's not clear at all. Minus 4/3, why shouldn't it be minus 8/13? Well, it's minus 4/3. And then what happens is you again get subcritical and supercritical. Actually, here I'm doing it technically, but in actual, you can run this with n equals 10 million on a computer very quickly. Have your students run it. And you'll see that when lambda is minus 4, you've got tiny components. And the biggest components are all around the same size, and they're all trees or maybe unicyclic, but they're all simple. But by the time you get to lambda equals plus 4, I mean, technically it's approaching infinity as n goes to infinity. By the time you get to lambda equals plus 4, a lot of these tiny components have merged, and you get not a giant component, but a dominant component, which has size much, much bigger than all the other components. I would say a Jupiter, but actually, Saturn isn't that much smaller than Jupiter. I used to say Jupiter, but this dominant component that's much, much bigger than the others and has a complex behavior. And for any constant lambda, like lambda equals 1.3, you get a very complex behavior that's really interesting to study. And there's a wonderful gravity here that happens. If you think of this as a motion picture, and you have, at a certain lambda, you have these components. So you have like this asteroid belt of components. But then there's a strange gravity when you increase time by d lambda, from lambda to lambda plus d lambda. If you have something of C1 n to the 2/3 and C2 n to the 2/3, they merge with probability C1, C2, d lambda. So you get a very interesting physical phenomenon. And this has been a great discovery. And now the ties to percolation in mathematical physics are really deep and profound, and people are still working on it today. So at the start, the probabilistic method was counting arguments. It was interesting, Paul Turan, who's unfortunately I never met, we came in September and he passed away in October, but Paul Turan in number theory had the proof of the Hardy-Ramanujan result that almost all numbers from 1 to n have roughly log n prime factors. And he wrote it as a counting argument with summations. But today, we would say, you just pick a random number and look at the number of prime factors. So when Turan Paul wrote this paper, it was with summations. But today we would say, take a random number from 1 to n and look at the random uniform and look at the random variable of the number of prime factors and calculate the mean variance. So what we would say today is pick a uniform random number from 1 to n, then the number of prime factors is a random variable, and you compute the mean and variance, and then you just say the variance is so small that almost surely it's near the mean. But that was the days when maybe it was the probability was not considered real mathematics. I don't know. I mean, if you go back far enough, probability isn't that old a field. Anyway, that was the case. So a lot of the probabilistic method was really counting. And then there were two breakthroughs that I put together, though the results were quite different. And one was by Lotzi here, and the other was by Svante Jansson from Uppsala. And these, I think, were very important both for themselves, but they showed that you really want to use some serious probability when you're doing the probabilistic method. So here, in both cases, the framework was quite similar. You had a bunch of bad events, and then you wanted to look at there being no bad event, like a sieve. So sometimes I call your result a lovasita. So, and so what can you say about the probability that none of the bad events occur? And suppose you know which pairs of events are dependent. Although you have to be careful, there's a technical definition there that's not quite the usual definition of dependent. And the Lovas result was that if each bad event was only dependent on a few other bad events, then the sieve worked, and the probability that none of them held was non-empty. And so this was a great extension of the basic Erdős argument. In fact, that's what Yanni referred to my result on Ramsey KK. And it's true, it's the one that's quoted most, but I think it must be the cheapest result I ever had, because Lotzi wrote me about the result, and I just applied his general theorem to the case and got the new upper bound on Ramsey KK, but sometimes that happens. So there was a great extension of the Erdős Csoda. And the other one was by Svante Jansson, which again, if the dependent events weren't too many, so sum over the dependent events, dependent of pairs was small, then the probability that all of them held, that none of them held, was as if they were mutually independent. And so I think these two results were very important, both, like I said, both for themselves, but also to say that there was real probability behind the probabilistic method. It wasn't simply counting. There was something more to it. At least that's the way I thought about it. One of my favorite problems was Ramsey 3K. That is, so you have these n people. Well, let me talk about, a graph on n points, and there's no triangle, and how big an independent set can you get? And this was something that has a 90-year history. It really started in 1931-32 with Értesülj and Székfoglaló looking at it, and we're still working on it today. So I love problems that are where, I mean, there are plenty of problems that for 200 years nothing happens, but in this case, for 100 years, there were improvements almost every decade, and so it's a wonderful story. So the question is, how big should Ramsey R3K be? And Értesülj in now I'm forgetting the year. It was quite early in the 60s. He had this fantastic result where he got close, but it was off by a logarithmic factor. Then there was a very important result by Komlos and Samaretti that it turned out did get the right result, but it was just in one direction, not the other direction. But this was a big result. And then finally, the value of R3K, which you can see on the bottom, turns out to be K squared over log K, was found by Jean-Han Kim, although he had a poor constant for the bounds. But what we think now about it is the following process, the random triangle-free process. So we take these endpoints, and in the beginning there are no edges, and you take the n choose 2 pairs and you order them randomly. So that's the only randomness. You order the n choose 2 pairs randomly, and now you consider them sequentially, and you put them into the graph unless that will make a triangle, and then you don't put it into the graph. So it's a very simple procedure. Each edge comes in, and you either put it in if it doesn't make a graph, and nothing else. You don't do anything fancy. If it's going to make a triangle, you don't put it in, so you'll never get a triangle, but otherwise you do put it in. So this we call random triangle free. But the key thing is that the n choose 2 potential pairs are ordered in a random order. So sometimes we call it random sequential. And then you want to just study this very interesting process. And it turns out there's so many people. I mentioned Tom Bowman was one of the first, Kivash, Griffiths, so many people have worked on this process trying to understand it. And it turns out that it can be modeled by differential equations, but then there are really problems that you have a differential equation, but you have a random process, so there's stability problems because things are just going all out of whack and you don't know what's going to happen. But they managed to do the analysis for quite a long time, and with it they showed that if you use this random triangle free graph, you'll get a graph that does not have a large independent set, in particular square root n, square root log n, and that gives the best known result on Ramsey 3K. It's now known within a factor of 4, so any further result? Well, maybe the next 10 years we'll see what happens. The birth process is quite famous. You start with Eva, and every node has a Poisson. It could be another distribution, mean lambda children, and so it goes down and down, but of course it might stop. And what is the probability that it does stop? Let x be of course it depends on lambda. What is the probability that the tree will be finite? Well, you have a recursion for that. So this is standard stuff that I teach to sophomores. If x is the probability that it's finite, if Ava has k children, then the probability is x to the k, because all those k children have to have finite trees. So you get a recursion that x is the sum over all k of the probability that Ava has k children, well, it's Poisson, times x to the k. And so you get a nice recursion, a recursive equation, and you can look at that equation, and something very strange happens when lambda is greater than 1. There are two solutions. One solution is that x equals 1 is a solution to this equation. But there's another solution, which is that x is less than 1, that there's a probability that the tree goes on forever. And that turns out to be the correct solution for the problem. When lambda is less than 1, there's only one solution, and that is, as your dear Prime Minister knows very well, that the end is coming. Lambda is less than 1, and the tree will eventually disappear. But if I can make a weak joke out of it, there are actually 2 points of view of this. There is axiom A, which is that more people are good and fewer people are bad. This is held by an unholy trio consisting of Elon Musk, Viktor Orban, and the Pope. I don't think there's anything else they all agree on, but that's one. And then there's axiom system B, which is that more people are bad and fewer people are good. And this is held by Malthus and Deng Xiaoping, the old Prime Minister of China, and many environmentalists. So what is the solution? Well, again, alazatosh velemenem serint. This is the continuum hypothesis. This is the continuum hypothesis of population dynamics because both axioms give you consistent theories, but they give you very different results. So, however, let's now turn to other events, and I want to talk about my wonderful student, Mumanti Potter, who's now a professor of mathematics at IISER Pune in India. And she considered other properties that also give a recursion. Just to be, recursion there's some technical things about what you mean by the recursion. For the logicians, these are monadic second-order sentences, whatever that means. And what she proved was that if you take any first-order sentence, again, whatever that means, you'll get this recursive equation, but it will have a unique solution. It won't have a second solution. So rather than doing this in general, let me just take the example of the property A that nobody has exactly 2 children. So there's a property. What is the probability X that nobody has exactly 2 children? Well, X, you sum, if Ava has K children, well, either K equals, you want to say that no node has precisely 2 children. So you sum over all K when Ava has K children, except for 2, because you want no node to have it. And for each such K, the probability is X to the K. So again, you get a recursion. And actually, this would be a very nice calculus exercise, except I don't know how to do it, to actually prove from the calculus that when lambda is greater than 1, that there's a unique solution here. But the argument of Potter used the following idea. You look at a property and you say that it's finitely decided if almost surely there's a cutoff. Now, the cutoff depends on the tree. It's not a fixed size cutoff. If almost surely there's a cutoff, so that by that cutoff, you know the truth value of the statement. So being infinite is not finitely decided, because even if you cut it off at size 1 million and you have 8 billion nodes, you don't know absolutely that it's going to be infinite or not. But it turns out that every first-order statement is finitely decided. And in the case of having exactly 2 children, well, there are 2 cases. Either the tree is finite, but if the tree is finite, it's finitely decided because if it goes down to level K, by level K plus 1, you know exactly what the tree is, so you know the case. So it is. But on the other hand, if it's infinite, not hard to show that an infinite tree with probability 1 does have something with 2 children. So you just go down to where there's 2 children, and now you've decided that it has. So this is the case. And then it turns out that she was able to show that once it's finally decided that there can't be two solutions, X and Y, for that. But I think rather than do that, I want to go back and finish by talking about these three wonderful people who we knew so well. Let me start with Hoyno Andras, who, of course, many of you remember was the igazgató of the who was the igazgató of the Matkutato Intézet. Andras was a great logician and great combinatorialist, but for Marianne and I, he was just a wonderful friend. I think when we come to Hungary, we so often are able to laugh and smile and joke and have a wonderful time, and never more than when we were with Andras and Emmy, if I remember right, her name. Yeah, Andras and Emmy. They were just two wonderful, enthusiastic people, and they were two people that really made our time in Hungary very special. And then Veronka. I mean, I could talk for an hour about Veronka. In her time here and in the United States, femininity and science were often difficult to reconcile. But Veronka was always the great, great exception. She was a great mathematician, she was a great lady, and she was a great leader, and here I'm talking to people that know far better than I. She was a great leader of Hungarian mathematics for many, many decades, and we still miss her dearly. And finally, Pali Bácsi. Again, I could speak for an hour about Pali Bácsi, but the mathematician chronicler ezt mondta, hogy die ganze Zahlen, der liebe Gott hat die ganze Zahlen gemacht, alles anders ist Menschenwerk. Menschenwerk. Erdispál munkája. Nekünk a munkánk. Nagyon köszönöm szépen. So proud. I'm really honored.